for the second session on Clojure. So I think that's the follow-up session. I'm really excited for being here. So with Mashooq, all of you, with Elder as well, all of you. And as always, just before we start, if you're new here, we have the session, the previous session recorded, available on YouTube, where we went through the basics, let's say, of the language, and then we ended with the FizzBuzz kata. So it was really an interactive session. And today, I think Mash will give more context, but I think that we expect to have an interactive session as well, right? So we are going to be following you along. So yeah, so thanks for joining. And I don't know, Elder, do you want to say a few words before we start, or before pass to Mash?
Yeah, sure. Thank you. So thank you all, and thank you for this new session of Clojure. The last one was super great, from zero to FizzBuzz. So I recommend very deeply to see the recording on the Codurance channel. It was super great. So take a look, put a like and subscribe, and all the things that we always do in YouTube. Also take a look of the communities, Codurance meetups and Software Crafters Madrid meetups. We have plenty of things now discussing things not only on technical part, but also in management part. So take a look. Even tomorrow we will have a new one created with functional programming also, but with a different language. It's PHP. So we'll be super curious, mothers. So that's all from my side for now. I will be pasting some URLs on the chat in case that you want to take a look of the meetups and the groups. And that's all from my side. So it's all yours, Mashooq.
Thank you, Elder. Buenas noches, todo. So yes, I hope that you, well, the ones that who were in the previous session, I hope you enjoyed it. This one is going to build on the previous session. But if you haven't seen the previous session, don't worry. You can always catch up on this one. The idea is for you to join so that you are trying the things that I am doing. That's why I will be typing everything from scratch almost, so that you can follow along. So you can type things. So if you have two screens, or maybe create a split screen with me on one side and your own editor on the other side, and try those things. Also, as previously, this session is an interactive one. So if you have any questions, or if you want to try something else, just ask, right? You can ask any question you like. If the question is too advanced, I will say it's a bit advanced. I may answer it if I know the answer. And if I don't know the answer, I might say that it's too advanced, or I might say that I don't know. But the main thing is to enjoy it, right? To enjoy the learning process. And yeah, interrupt me as much as you like. Yeah. So what I will show you first of all is what we are going to cover. So in terms of, so previously, just to give you a bit of, in the session one, we covered what a REPL was. We looked at the basic types and keywords and so on in Clojure, how equalities are done, how Clojure works on code as data and data as code. It's built on the JVM, the Java Virtual Machine, so it integrates with everything, integrates with everything that Java has, all its libraries and so on. So I showed you a bit of that and how to leverage the libraries that we already have in Java. Then we started looking at some of the native data structures. We didn't go too much into the detail and some of the conditionals, functions, and then we went into a small kata, which was the FizzBuzz kata. Yeah. So that was the session one. So in session two, we are going to look at, we're going to carry on with the native data structures, but this time we're going to go a bit deeper, really into kind of what is the basis, or not necessarily the basis, but bread and butter, as we say in English, of a functional language, right? See, these kind of list operations or list comprehension around map, filter, reduce, these kind of things. We're going to also look at sets. Clojure has a data structure of sets, which is actually can be quite useful. And then we're going to look at maps. And maps is really the engine of how data is represented in Clojure. We may look at record, but we may not. Maybe I'll leave the record side of things to session 3 for now. Then we will revisit our FizzBuzz and see if, given any of these new things, people actually mentioned it already, can we add and make it a bit better here and there? Then we are going to talk about functional paradigm, right? Just a little, not too much. Again, sorry, I can hear myself conscious.
Yeah, there.
Thank you. So basically the functional paradigm, exactly what makes a language really functional. We'll look at the Wikipedia definition of functional programming, and we'll see how that applies to some of the work that we're doing. So just to kind of start introducing you to the functional paradigm itself. We will then look at deconstructing, which will become clear to you later. And if we have time, we will go more further into list comprehension, which we did a bit of that last time. And we might look a bit more into the functional paradigm around partial functions, currying, and CURR, currying and closures with an S, not with a J, right? What they mean as well, right? So this is the kind of thing that we are looking to cover. We might not get to all of it, but that's okay. We have a few more sessions to still go, and we will revisit some of these. So if there's any repetition, remember we learn through repetition, so please bear in mind. Yeah, cool. So without further ado, we talked about getting the REPL started. So you should have Clojure tools installed, and CLJ allows you to get the REPL started. Yeah. So we were talking about lists, maps, filters, reduce, pop, peep, and group by. So let's create a list and see how this map and filter kind of things work. And now, if you're not used to functional paradigm too much, or haven't used the functional aspects of all programming languages, you might get a bit lost in the terminology, but feel free to ask. Yeah. So let's start with creating a list. So we've got a list called X, and we're gonna create its elements 1 to 10. Yeah. So that the range function allows me to create the elements, and basically this is like a variable in any language, and it's assigned to X. So I can refer back to X again now, and you can see that I have a list of elements 1 to 9. Yeah. Okay. So now, what does map do to this list? Right. Map basically takes a function and applies it to each element in your data structure. That's what it does. So normally if you wanted to do, so for example, if I was to tell you, take each one of these elements and then create another list that increments each element by 1. Yeah. In a empirical language, what you will do is you will probably hit a for loop. You'll say, your list is X, and then for I equals 0, I smaller than X dot length, I plus plus, or something like that. Or you might use a for each loop. Yeah. You'll create another data structure, have a list X and list Y as the list that you will create the other thingy. And then you might even keep changing what is in X, right? But let's say that we don't want to change X. So you will add, for each element, you will add, increment that element, and you'll add it to this new list. Yeah. And that's how you normally do work in imperative languages. In fact, what I'll do is I'll show you if you. So like for example, in Java, you might have, int x equals, and then you will have this, this list of 1, 2, I think it's like this, 3, etc. Yeah. And then, of course, you'll have the semicolon. And then you may even have int y equals new int x dot length. Yeah, because this is where you want to store the new stuff, semicolon. And then you'll have for int I equals 0, I less than x dot length, I plus plus. Yeah. And then what you will do is you will then, in there, you will start saying, okay, y I equals, sorry, it's my Clojure editing tools are not like in Java at all, but you know what I mean. So it will say y I, yes, it's not liking it, but okay, you know what I mean. Y equals, in fact, I can do this. I can make it a comment. So y I equals, and then you would say, so in this case, we are incrementing, right? So we can say x I plus plus, like this. Yeah. So now, once the loop has finished, you will have a while loop where you will while collection that has the incremented list. Yeah. So this is an imperative style. It's not the wrong style or anything. And in fact, one can say, well, in Java and so on, we can now use different styles of doing the same thing, or we can do a for each. And so yes, you can, right? But originally, this is the imperative style of performing the same thing that we are going to now do in a functional style. Yeah. So in a functional style, you actually map, right? So you can map over each element, as I was saying. So let's first of all look at document the map function. As I was saying to you last time, you have this doc function in Clojure that allows you to understand exactly what map does, right? Or what any function does. So in this case, then it returns a lazy sequence. Don't worry about the lazy sequence. In the next session, I will talk about laziness as well. Of the result of applying f to the set of first item of each collection, followed by applying f to the set of second items, and so on. So f is the function, and it will apply that to each element of the collection. That's what it's saying, right? So our collection is x, right? So in now, what I can say is, okay, map, and then I need to provide a function. So you can actually say there is in fact, let me do a doc on inc. Increment is a function already available to me in Clojure, right? So I can refer to this function. I can create my own increment function as well. It's not that difficult, but it's already exists. Returns a number 1 greater than the num that it takes. Yeah. So what we will say is that, like for example, if I say int 2, it will give me 3. Yeah. So now what I'm doing is I'm saying map int is the function. So I'm referring to increment as the function. So I'm saying apply this function. Yeah. On the collection x. Yeah. So what should I get back?
2. I guess 2, 2, 4. If you have 1, 2, 3, 4. Yeah. If you have 1, 2, 3, 4, I think it would be like 2, 3, 4. Starts from 2.
Yeah, exactly.
There we go.
Yeah. So yes. So functional style is powerful. This is why Clojure is so succinct, right? And most functional languages are so summarized. They look very small. Basically, I'm doing what lines 16, 17, 18, and 19 is doing in map int to x. Yeah. In fact, there's 2. I lie because actually there's 2. I'm defining X, and then I'm mapping into X. Yeah, these are the two things. So as you can see, this is what map does. Map is basically taking any function and applies it to a list of elements, right? And returns you another list that is the result of each application of the other elements, right? So the result of map is always the same number of elements that you put in it, right? They just transformed. Have I lost you? Or does that work? Yeah, cool.
So far so good. Yeah.
All right.
Just have one question, Mash, because you use range. So I assume that this is a built-in function, I guess, from the language.
Sorry. Yes.
Is that correct?
Range is a built-in function. It's just a handy function to return a sequence of numbers from start to end. And you can also define a step on what kind of step to take. Yeah. It's actually, again, a lazy sequence, but I'll tell you about lazy sequences later. Yeah.
Okay.
Lazy sequences basically allow you to represent infinite lists. So functional programming languages allow you to deal with infinite data sets. Yeah. But again, I'll stop there. Right. So then what we are going to do is the other side of map is reduce. So a lot of the times you see this map and reduce, right? So reduce basically takes a collection and applies a function that actually summarizes the collection into a single result, right? So for example, like plus is a reduce operation. Reduce operation is any operation that basically takes each element in a particular collection and applies a function that is creating of the two, creating a single result, and then applying that result to the next one, and so on and so on. So sum is one of them. For example, if I have X in this case, I can say, well, sum all the numbers. What we'll do is it'll sum 1 plus 2, that will give me 3, then 3 plus 3 will give me 6, and 6 plus 4 will give me 10, and so on. And he keeps summing them until I have the whole sum, and I get the sum back. That is referred to as a reduce function. Yeah, it takes any list and gives you a value back. So let's doc reduce. What is it? And so again, sometimes the documentation talks a bit more in functional language terms. So in reduce, what we are saying is that f should be a function of 2 arguments. If value is not supplied, blah, blah, blah. So, okay, this is just telling you how the reduce is going to be used. But basically what it does is, for each function has 2 arguments. One is the accumulator, the next is the next element in the list, and it creates the accumulator. Now, in empirical languages, you will do this like, you got an X like this, and the way you will have this is you'll say int sum equals 0. Yeah. So then what you will have is sum plus equals xi. So this is how you would do it in this case. So you say, so that's my cat. Can you hear that? He also wants to call. Just 1 second, let me get it out.
All right. That's good. This is we can pair with him. All right.
Yeah. All right. So after that brief interruption by my cat, let's talk about reduce again. So in this case, as you can see, that it will sum each thing, and then we have the sum back. And again, this is the imperative style of doing this. In the Clojure, in the functional style, you'll say reduce, and we apply a function. So plus, by the way, is a function, and I can say doc plus, and see, it's a function. Everything is a function in Clojure. Clojure has one of the fewest native language elements. Everything is a function, right? So I can say, for example, plus 1, 2, and will give me 3, right? So now I'm saying reduce plus to X, which was, remember my list, gives me 45, right? So what it's doing is applying plus function to each element in the X, creating the accumulator and giving me that result back. Yeah. Again, much simpler in the functional style than you would do in a imperative style. Yeah, cool. Any questions? No?
Not so far. So far, so good. Very good to.
Okay, cool. And by the way, I'm sure like some people would, you know, this is basics, but this is a basic functional programming and Clojure course. Yeah. So bear with us. If you find these things quite basic, remember that some people may not know about it at all. Yeah. It's only basic if you know. Right. So we are talking about, there are other things that you can do to lists and pop peek that allows you to do kind of operations that you would do on a stack data structure, for example, in Java or C#. So if X is this, and then I can say pop X. So the new list queue without the first item for a vector. Okay, so I need to give it a vector for pops and rest, because lists don't work in the same way. So let's create a vector, which I was showing to you last time. It's an index array, basically. That's what a vector is. A list in Clojure is a linked list. Yeah, so it can't form that thing on that, but it will work on that vector. So that's why vectors, and I can say 1, 2, 3, 4, 5, and so on. Yeah. So then I can say pop Y, and see it pops the last element of Y. Yeah. So what I get back is the first 4. If I say P Y, it gives me the last element. So this allows you also to, and you should be able to do it on the lists as well. Let me just see. Oh, because that may have been, that was a lazy data structure, that's why. So def X, if I say 3, 4. So this is how you represent lists, as I told you in the last thing. Yeah, so this is my list. It's no longer lazy. I should be able to pop X off this list of X. Yeah. The reason I got the other problem is because that was a lazy data structure, and pop takes the last thing, but the lazy data structure is infinite, right? But in this case, I have created a structure that's not lazy, and it's giving me. So, and then if I do pop in this peak in this case, it should give me the first one. So as you can see as well, they are slightly different in this case, because if you see that in a case of a vector, when I did a pop, it gave me the last element. Sorry, it gave me everything but the last element. And in the case of a list, it gave me everything but the first element. Yeah, that is, as I said to you, list, the way they are structured is they have a single pointer, and each one is a linked list. Yeah, and the pointer to it is the first element of the list, right? So when you take something, when you pop it, the easiest thing for it to do is to pop the first element. So for list, it will give you the first element. Vectors are random data structures and they're indexed. So for that, it can give you the last one. And so it does. So they are optimized for different kind of operations. If you, depending on what kind of operation you want to do, you'll use lists versus vectors. Vectors obviously maintain indexes as well. So they are larger data structures, whereas lists are more efficient data structures. Yeah. And these are things that, like, especially in Clojure, when you start talking about data structure, you need to know exactly what each data structure is designed for. Okay. Any questions?
Not from the chat, but I do have one myself, regarding this, the list that you shared. So is it recommended, for example, to convert a vector to lists or to do such operations? or is better to start with the correct data structure?
You can convert a vector to a list if you need to. And in fact, certain operations will give you a list by default, even if you give it a vector. Yeah. So for example, I think, and I might be wrong, but I think, like for example, the map function that we did, let's say our vector is y. And if I now do a map on y, see, I get a list back. Yeah. So then you can, from what again, I've not tried this for a while, but if I say into, I think into gives you a conversion.
Okay.
Right? So now you can say into vector, yeah, map in y. See, that will give me a vector back. Yeah. So map always gives you a list back, but if you really want it to be still be a vector, you can convert it back into a vector. Yeah. Again, these are all immutable data structures. So you're not converting the same thing, you're creating a new thing. But Clojure is very good at copying data structures. And that's something I can show you in the next few sessions as well, how Clojure is so good at efficient data copying and data structures, because like in an imperative language, every time you add something, you copy the list. That's not going to be nice. Whereas in Clojure, that's actually done by default by the language itself, and it's super quick, quicker than it's the Java data structures. Okay, so the other thing I can show you is group by. So group by basically allows you to create tuples. A tuple is a logical grouping of elements into a data structure. That's what a tuple means, right? They are data structures that associate within themselves, right? So for example, again, if I look at X is 1, 2, 3, 4, 5, I can group that by a function. So odd is a function, yeah, or even. So let's say group by or divisible, yeah, even or not even, yeah, and X. So it's saying it's grouping, so it's returned to me a map, yeah, and map I will show you later, but basically it's key value pairs, yeah. It's returned to me a map where it says group by even was false for 1, 3, and 5, and it was true for 2 and 4. Yeah, so you get this logical grouping through the group by. Again, these kind of things when in the real world can be very useful as list operations. Yeah, doing this kind of thing in imperative style, you have to have those two data structures, you have to have if conditions, conditionals, and you have to then accumulate the data in those two separate lists and so on. You don't have to do any of that in Clojure. Okay. Interesting. Any questions before we move on? No?
No question. So far, so good.
By the way, are you guys trying this?
I'm trying. I'm following along. Actually, and people that is joining us is recommended to also try to follow along. Actually, now that you that you're saying, we have this even and question mark. I guess this is from Clojure as well, right? So
yeah. So even question mark is a function.
It's okay. So I guess that it's odd. A wild guess that we have an odd as well. Is that correct?
Yeah, exactly.
Okay.
So Clojure, there is a convention in Clojure. The question mark is just part of the name. Clojure has question marks at the end of the function if it's going to return a true or false. Yeah, it's just a convention that Clojure applies. It also has the exclamation mark that actually gives you this one actually gives you, it tells you that this function mutates state. Yeah, it has side effects. So normally the convention is that if you have a function that has side effects, you prefix it with the exclamation mark. And if you have a function that returns a Boolean, you will prefix it with a question mark. Now, if you don't do it, it's not going to say anything to you, but it's a good convention. Yeah. Okay. So now, sets. The way sets work are basically, so let's say def s is, so this is how you define sets. Sets are distinct unordered lists, yeah, which means that every element is unique within a set. So you can't have a set that has an element that is repeated. If you try to repeat that, it will deduplicate it and just give you one instance of it. That's what a set means, right? But it's unordered. Yeah. See, when I store it 1, 2, 3, 4, and 5, it's actually giving me 1, 4, 3, 2, 5. Yeah. It will store it according to its own ways, and you can do nothing about it. Yeah. It's an unordered list. What you can do on sets is that you can do like lots of things like intersections and unions and all those kind of things, you know. For example, if I say union S with another set, I don't know, 2 7, 8, it will union that set for me. A lot of these things I haven't tried. How does the union work? Union. Sorry, just bear with me. Union set 1, set 2. Yeah. Union. I am spelling it right. Oh, that's
Yeah,
why, because it's in a enclosure set, my bad. So what you have to do is it's in a different namespace. It's not in your current namespace. So you have to do Clojure dot set union like this. Yes. Clojure set union. That should be correct. Okay, so I'll get back to this, but it's in a different namespace, and it seems that I can't get to that namespace. But you can do intersections, unions, all those kind of things. I'm just can't remember the exact syntax for it. Yeah, I think it should be Clojure dot set. No, I can't find it, but that's fine. All right, but you get the picture. So the other thing is with sets is that you can do like contains and that kind of stuff on sets. So you can find out if it contains a particular element. So for example, if I have a set S, you can use the same things. Contains like let's say let's do dot contain first. Yeah, so it takes a collection and a key. Yeah, so in set the element itself is the key. So if you do contains in set S key, let's say 4, it's true. But if I say contains key, I don't know, 8, it will be false. Yeah. So you can find out, you can, and these are again, because they are distinct, they are kind of key, they hashed values, the lookups are extremely quick. So when you need to do lookups on certain things, you should be using sets. So for example, all the keys of a hash map is a set, yeah, because it's hashed and it's very quick to get to that particular element. Yeah. Okay. So that's sets for you. We'll move a bit quicker because there's a few things. I will, so now maps. Maps are the most common data structure you find in Clojure programs, yeah? So a map is basically a set of key value pairs, yeah? And, sorry, just one second. Yes, so the way you define a map is by curly brackets, and you use the, remember I introduced you to keywords, which start with a colon. They're almost like enumerations or intern strings in Java, which basically means that they're very good at keeping as keys. They evaluate to themselves if you use them as a literal, if you know what I mean. So they're very fast data in terms of a comparison between two keys of the same type. It's very quick. The comparisons are by memory and not by value. So they're very, very quick. So they make really good fast keys for hash maps and elements for sets. Yeah. So for example, in this case, let's say I have a data set. I'll call this X again, and you define it like this, and say name is Mash, and surname is right. Now, as you can see, so this is how you keep data structures. In Java and other languages, you create an object or value object of some sort. In Clojure, you can use records as well, but I'll go into that in the next session. But the primary data structure for maintaining structured data with names is a map. So you can have maps inside maps, you can have lists inside maps, and all those kind of things. This is the simplest data structure we have, right? So this, then you can work on this in any way that you want. And the way that you can say, for example, if I want the name from X, I can say like this, name X, and it'll give me the value of that back. Yeah, I can do contains as well on it. I can say, for example, but it will contains on the keys. Yeah, so I can say contains name in X. Oh, it probably is the other way around. I think it'll have to be keys. So that's true. So it says that, you know, X contains name. Yeah. But if I say X contains, no, it's false, right? So you can do on the contains, and you can also do it on values, but then you have to extract all the values from the map and then do it. But the values function allows you to do that. So if I do dot values, there is another function that allows you to get the values, and then you can do it. But again, the values themselves are less important in this case, and also it will do a sequential search on it. Normally, if you keep maps, you don't really think about the values. You first get the value out, and then you see what that value is, right? So
just a quick note, Mash,
Yeah.
before you jump. I think the values is vol. I think the word that you're looking for is vol. Those is
Val,
returned
sorry.
vol. Yeah,
Well, like this.
I think so. I'm just guessing because
Yeah, there you go.
there
You're
you go.
right. It's been a while since. So if I do val on X, no. Yeah, X is a map and returns the value in the map entry. Sorry, the value is not the same. What that
it's not the
does,
same.
it does the same thing as what I did, because if you look at val, is like this. So if I return the value in the map entry, yes. So no, I think it's basically the same thing as I did here with name. So you can actually use the keyword as that function to get the value out, but it doesn't give you all the values. Yeah. Okay. Anything else on the map? I'm gonna revisit maps for destructuring and those kind of things, but basically, if you want to represent a data structure, you use maps. Any questions? No?
So far, so good. No, just to share that Elder shared a link with the coding for people that want to double check as well. Just to, a minor note. But yeah, no
Okay.
questions so far, so good.
Actually, let me just see how map. Yeah, I think you can get values from a map, but I'll have to look that one up. I'll show you later on. Yeah. All right. So moving on, we've got let's revisit the FizzBuzz and make it a bit better, because I think it was someone who said to me, why are we using list comprehension, like the for loop that we were using, like in this case, like that? Why don't we use a map? And they were right. So for going back to FizzBuzz, let me remove this. Okay, so going back to FizzBuzz, we have this function that actually, in fact, this was, by the way, you have to do a FizzBuzz if it's divisible by 3 and 5, and not just that. But anyway, not divisible by 15, because I was looking at this and I thought this is wrong. But anyway, so we have the FizzBuzz function, and we can put that back in there, and we can say, well, FizzBuzz, what does that do? If I have def x range 1 to 50, let's say 18, and then I say FizzBuzz x, so it will say 1, 2 phase, 4 buzz, and so on and so on. Yeah, as we talked about this, and we saw that this particular, in this particular case, what we had was we were using a for loop, for statement in this case. Yeah, and someone asked, well, why can't we just use a map statement in this? Yeah, and we can. So just to refactor this a bit more is that, you use a map, but the way to then use the map is to say, well, okay, we have to create a function that does this FizzBuzz, and then we create the map over it. Yeah, so map, and then you have to provide the actual namespace, the actual list. So we map over that, and the rest needs to be a function. Yeah. So what we can do in this case is like this. This is a way to define anonymous functions. So now everything between the hash is an anonymous function. You can actually define it in a different way as well. And I can maybe show you how to do that. That might be better. So actually, fn takes in n, yeah. And then I can take the whole of this body and put it in there. This is when knowing Vim shortcuts helps a lot, because it's block editing. So you can add it using those brackets. So when you start using when you start programming in Clojure in Anger, block editing is a skill that you must have. What I mean by block editing is basically I can say, take everything in this block and copy it, for example, or delete this block, like this. So I've deleted the whole block, or I can say, take, delete everything inside the block, or keep the brackets and stuff like that. So I can do all these things, and this is structural editing. And it allows me to not make any mistakes with the brackets and that kind of thing. But in this case, what we've said is we're introducing a mapping. Actually, this has to go right at the end. Yeah. So, yeah. So now what we're saying is we're taking a function, we're defining a function in place. Yeah. And we are mapping it onto the numbers list. Yeah, and if I am correct, I can put this in here again, and I can rerun this function. Yeah, so FizzBuzz x, and I get the same value back. So this is basically an equivalent function that I have used map with. But as you can see, that this is actually not so readable. Yeah, so you can actually define another function, and you can say define a FizzBuzz. Yeah, and you can say, well, this takes a n, and I can basically put this, the value of this condition inside there, right? There, like this. Now I can delete this. And I can say apply if is best to everything. Yeah. Okay. So now I know that if is buzz does this. Yeah. And I am now a secondary function that is applying over the whole of this collection, the if is buzz. Yeah. So I can do this. So let's say, yeah, so I have an if is buzz function, and I have a FizzBuzz function that uses a FizzBuzz. And now if I say FizzBuzz X, I think that's what it was. Yeah, I get the same result. Yeah. So I've made the function a bit more readable by extracting things out. You can, what I will show you in the next session is how to use Clojure threading macros where you don't have to define functions outside and you can still keep it nice and readable. And I will also show you partials to make it even more readable, those kind of things. Yeah. Okay. Any questions? And are you following along?
Yes, we have a question from Luis. It says, do you suggest to use Paredit? I don't know what is it for that, or would you suggest other tool? The question came out when you were editing, talking about the blocks, if I'm not mistaken.
Yes, yes. So basically what Paredit does is it allows you, so if you have Paredit, it stops you from removing brackets, yeah? So for example, I'm trying to remove this bracket, but it won't let me, yeah? Because if I remove that bracket, it will be, it will not be a correct form anymore because I have a starting bracket but not an ending bracket. So Paredit allows you to only keep, so that's why when I was writing imperative Java code in here, I wasn't able to, yeah, because, and that's why I had to put that in a comment, because Paredit is stopping me from making any errors in terms of starting and ending of brackets. Yeah, so yes, I use Paredit and I recommend you use it, but not until you get a bit more comfortable with editing, because it can be a bit off-putting as well. It stops you from deleting code in certain ways, and if you use only imperative languages, that can be a bit off-putting. Yeah.
Okay.
Any other questions?
Nope.
Cool. All right. So let's go now to, I will talk about records actually in the next session, because I think we still have quite a bit to cover. So let's go to the functional paradigm itself. So there's a bunch of, so what makes a functional language functional? Yeah. And how do you describe the functional paradigm? And the way I looked at what I did was I went to Wikipedia, like we all do, and see how do they define functional programming. And what I want to do is actually describe to you in terms of what we've been learning so far on what the functional paradigm is. Yeah. So functional programming, so let's take this definition and break it. Yeah. Is a paradigm where programs are constructed by applying, sorry, things are in the way, by applying composing functions. It is a declarative programming paradigm in which function definitions are trees of expressions that map value to other values, rather than a sequence of imperative statements which update the running state of the program. Yeah. Now, this is actually a big mouthful, but what he's saying is, at the end of the day, is saying that you don't have state mutations in functional programming. That's basically what he's saying. As soon as you stop dealing with state mutation, you automatically start programming in a declarative style and not an imperative style. Yeah. So as I was saying to you previously, we were talking about this, taking X and mapping over X. But then when I showed you the imperative style, what was imperative style doing? It was taking X, creating another list called Y. The Y is already a data structure, and then it's adding to that list. So Y is a state that every iteration in your for loop is mutating. Yeah. So that's a imperative style. In functional programming, you don't mutate, you transform. Yeah. So every data structure that you have, you transform it into another data structure. You don't change the data structure that you have. This is how it always works. Yeah. So that's why things like recursion and so on are quite important in functional programming, because recursion allows you to not have even a lot of these functions that I'm using, like map and reduce, they use recursion. Yeah. And in the next session, I will show you, like we just did map, I will show you how map translates to recursion. Yeah. Because recursion is the very basics of functional paradigm, functional programming. And what we are going to look at is how recursion is equivalent, because recursion allows you to not have changing state. It uses the call stack of the programming language to hold the data. So you're not yourself holding that data. You're not putting that into a list and amending the list over and over again. You're using the call stack. And in functional languages, they have this thing called tail recursion, which I will also, or tail recursion optimization, which I will also show you, which actually means that this kind of operation is super fast. The compiler does it much more efficiently, because you might think, well, if I have a very large list and my call stack is just going to be blow, right? And of course, in a normal way, it will. But tail recursion optimization in functional programming allows you to not do that. It's internally optimized to be able to deal with immense amounts of or really large size collection sizes. Does that make sense? Yeah. So basically, what the paradigm says is that you apply functions and you compose functions in a declarative style. Yeah. So we were applying functions, as you can see. Sorry, just going back to this. Yeah. We were applying functions, right? When we were doing map, we were saying def x is range 1 to 15. Yeah, we are creating x. Okay. Why is that returning anything? Oh, sorry about that. Okay, so we are creating x there. And then we are saying when we want to increment and get everything back, we are saying that we're creating a function for using already function already provided to us called inc, and we are applying that function onto x. And so if you can think about it, this can be a series of transformations. I can then say, well, not only apply that function, but I can say, okay, get me the, and we were doing the reduce, so get me sum the whole thing up. So what I'm saying here is, again, as you can see, this is declarative. This is not different to a mathematical function. You're saying map increment onto x and reduce the results of that with the plus function. Yeah. So again, see, you basically applying functions over functions. And going back to what it says here is programs are constructed by applying and composing function is a declarative style in which function definitions are trees of expressions that map values to other values. Yeah, that's what we are doing. It's actually a tree. If you really think about it, you got the root, which is map. In fact, inc is the first one, and then map is that one next, and then reduce the next. It's like a tree of function that you, or expressions that you are applying. In this case, it's just each one has a single child, and it's a very simple tree. but that's what we do. We are applying functions over functions to get our results, and we're not holding them in intermediate states and not changing that state and those kind of things. That's what functional programming means, immutability, right? It's a lot of people talk about a lot of things like what the functional programming does and those kind of things, but actually, ultimately, it's all about immutability, right? If you can have immutable data structures and you're not changing them in any way, and the results are also immutable, so you're not actually accumulating them in large kind of mutable lists and so on, you actually automatically have functional style of programming. There are other elements to functional programming like higher-order functions and so on, which we've been using a bit, but again, I will go into that in a bit more detail in the next session, because things are getting probably a bit confusing now. So I think for now, let's just concentrate on the fact that for a functional programming paradigm, we are talking about a declarative style that applies over values or over other functions. And with these functions are composed together in a tree kind of structure. Yeah. Does that make sense? Or have I lost you?
Well, it's interesting. In case that you want to generate any side effects on purpose, you need to use functions like random, for example, I think, don't you?
So random doesn't create side effects, but random is not a there is another word for that, for what random is. Random has a different property that makes it not functional. Let me just go back to what it was.
This is a different concept. You are talking about not doing side effects related with the state of an object. Instead, we are working on functions, and that grants you a little bit of not side effects for that. But in case that you want to generate some random behavior, you need to use things like random functions or seeds or whatever. Right?
Yeah. So I'll show. Yes. So if you want to create, is that what you're saying? If you want to create side effects? I mean, Clojure allows you to create a side effects. For example, the print function is a function that creates side effects. Yeah. So, or println. Yeah. See, it's what it's doing is it's returning nil, but outputting hello on the console. So it allows you to create side effects. Yeah. You can, strictly speaking, side effects are not functions. Side effects you move outside, but Clojure is actually quite pragmatic in that sense. It doesn't care, right? You know, in Haskell and so on, you really have to, in order to do any side effects, you have to learn monads, and Clojure doesn't care, right? Because monads allow you to move side effects to the outside of your program, right? Whereas, and that is purely functional because there's no side effects in the core of your program. In Clojure, you can have side effects, but like especially changing of state in Clojure is difficult. By default, you can't change state. I mean, you can, but it's like you can't really do much with it, right? And if you start changing state in Clojure, you're doing something very wrong. It will allow you to in some cases. I'll show you how you can do it, but it's useless basically. You have to learn how to use this function application with immutable data structures.
We have, I don't know if it is related, but Luis, when Elder said like side effects, Luis also shared it might be like impure. It's the same like the side effects in impure. Impure, yeah, impure. I don't know.
Impure. Oh,
impure,
I see.
Yeah.
I see. Yeah, you can. I mean, there are like, in order for a function to be pure, there's a bunch of things that it needs to have. One thing is no side effects, but also it needs to be idempotent. So, for example, random function that creates your random record is not a pure function because every time you call it, it'll give you a different result. So pure functions are, I think, are also idempotent, which basically means that every time you call it, it gives you the same result and has no side effects, right? So yes, pure and functions that don't mutate state and don't have so functions that don't mutate states are functional, but for it to be pure, it also means that it has no side effects. And I think there's one or two other things about it as well that I can't remember off the top of my head.
Okay, awesome.
Any other questions? We are now getting into functional theory.
No, just to remark that while you were talking, yeah, at the same time, Sergey remarked like idempotent. As well.
Idempotent.
Idempotent, yeah.
Yes.
That's a difficult.
Basically, you call a function 10 times, it will give you the same result, and it will have no side effects.
Yeah. So I mean, as far as I understand, that's what a random, random. I think is a random, right? When you generate a random, is not
idempotent because it gives you a different result every time you call it.
Okay, there you go. So that's it.
Yeah. Okay. So I think this is all the time that we have, and I wanted to cover a bit more, but it's fine because actually I'd rather cover less and for it to hone in. And I know that I went into the functional paradigm and started talking about immutability, idempotence, and so these things, I think it's good for you to just take that part because it's a very important part. You're talking about immutable data structures where functions are applied as a tree of expressions, yeah, to a data structure. This is the basis of functional paradigm, functional programming. If you get your head around that for this session, you are already on a good way to learning the functional paradigm. Yeah. And I think it's good to stop there because we are going to start talking about other things, but again, they are syntax related, but from a semantics, from a meaning perspective, just understanding what that means. Functions applying over lists, applying higher order functions that we're using to apply onto a data structure, these kind of things. This is the basis of functional programming. Once you get used to this, you are pretty much there. The rest is syntax. Yeah. So I will talk a bit more about composing functions application, partials, currying, closures, all these things, first class, higher order functions, all these things are functional paradigm terms, but they are just kind of a bit more sugar on top of what I just said. Yeah. So get your head around this immutability aspects, this application of functions as a tree of expressions. That's the main thing. Yeah. But in the next session, we will go through a bit more on using the FizzBuzz to kind of make it a bit simpler with other aspects. We'll go into a bit more into functional paradigm, into deconstructing data structures, those kind of things. And they are more related to kind of Clojure syntax. But I think we can stop here for now.
Okay, so that's awesome. So let me see. So if the chat has any question, the last one question, it seems like Luis just said, great, thank you very much. So it seems that, let's give it, see if people want to ask. So Sergey says, very interesting, thank you very much. So yeah, thank you for joining. No, so I think that's we are good to go then. So I think that's it.
Okay.
Awesome session. Yeah.
Yes, thank you very much, Mash. I think that for the next session we will have to wait a little bit longer because it's a January 11. But yes, we will be posting it, and also just to remind you that this session has been recorded and you can see this one and the last one, the first one that we did a couple weeks ago, also in a YouTube channel. I'm right now going to send you some links where you can also register to the next session. If there are not any more questions, I don't know.
Yeah, that's a good question. So Anna just asked if you recommend any learning resources, Mash, for this one.
Excuse me. Yeah, I'm just Excuse me.
Oh.
I've just added a few. Sorry, I lost my voice.
Well,
Yes, I've added a few there.
okay.
Where?
Yeah, so if you
On
can.
the chat.
Oh, okay. Excellent.
That's it.
So this is it. I don't know if you want to say goodbye or just thank everybody for being here. And we hope to see you in the next one.
Yeah, just to remark that.
Thank you, everyone. My voice is back a bit, but yes, I've added the Clojure columns. You can just do a search on, and also the book called Clojure, The Joy of Clojure. That's also quite good.
So that's it. Then also don't forget to double check the social media meetup for Codurance and also Software Crafters Madrid as always. And yeah, I think that's it.
Thanks, everybody. I think that Luis is also saying that Living Clojure is also a real nice book. So thank you, Luis, for that recommendation. And see you, everybody, in the next one. Thank you, Mas.
Thank
Thank
you.
you.
Thank you,
Bye-bye.
everyone.